Hello, everyone. So this week we started talking about Bayes estimators, but here I'm gonna recap what we said and then finish off this topic. Well, in fact, we hadn't done that much, so it makes sense to start again from the beginning. So we mentioned that this is a different approach to statistics in general, but in our case, we're going to talk about estimation of parameters. So what we said is that really the Bayesian approach to statistics is a different philosophy compared to the frequentist approach. So in the frequentist approach, recall we set parameters, they're fixed quantities, they're not random, but they're unknown, and we try to estimate them. But still conceptually, they're seen as numbers. It's just that we don't know what those numbers are. Now, in the Bayesian approach, we take a different view. We say, because the parameters can never be observed directly, we can really never be certain about their values. Because of that, we're going to say, okay, we're uncertain about them, and we're going to describe this uncertainty with a probability distribution. So we really view the parameter now as something that is random, that has probability to be between certain values. Okay. And we said in class that you can really visualize this like this. You might say, okay, this parameter I'm going to call theta. Even before I observe any data, maybe I have some expertise, maybe I have some preconceived idea of what theta is, or around where theta is. So I'm going to assign to it a probability distribution that represents this sort of subjective idea I have of what theta is, okay, of where theta is. So I might say, okay, it has a certain, we're going to call this the prior distribution. Okay, so G of little theta, this represents my prior belief. Okay, I think theta is around here. Okay, I think theta is around here, but I'm quite uncertain. So I assign a likelihood that theta is around this value to be kind of high, but I'm not certain about this. Okay, so maybe theta is here, but I think this is less likely. Okay, but it's still a certain probability that theta is around here, and then here it's still possible, but I just think it's very unlikely that theta is around here. But so we model the uncertainty we have about the parameter theta with the probability distribution. Okay, and as I said, this is what we're going to call G theta, the prior belief we have about this parameter. And again, here for notation, we call big theta just to highlight that we visualize it or conceptualize it as a random variable, then with this density G theta. Now because theta is random, we can write expressions for the joint density of observed data with the now random parameter theta. Okay, now so we use here the likelihood notation. So call big L of the data given theta, but here it's given that the random variable big theta has taken a specific value little theta, and we call this the conditional likelihood of our sample given that the parameter has taken a specific value. Now we call this likelihood just to highlight that it could be a mass and it could be a density, because those observations here, okay, they could be continuous random variables or they can be discrete random variables. Okay, so this is why we call this a likelihood rather than a density or a mass function. Now we still assume that given theta, the x's are independent of each other, which yields that this joint, okay, if the x's are all continuous, this would be a joint density. Otherwise, it's a joint mass. But in all cases, because the x's are assumed independent, to get the joint density of all the x's given theta, you just multiply the individual ones, okay? The density of x1 given theta times the density of x2 given theta, and so on. Now, because this theta is random, as we said, it has itself its own probability distribution. So careful that here, this thing is really in terms of a joint density of two random variables here, okay? the random variable x1 evaluated at the little argument little x1, and the random variable big theta evaluated at the argument little theta. Okay, and as we said, this prior represents the information we have about theta before any data is collected. Because here the point is this: we will use the data, but we don't want to only use the data to estimate theta. We also want to use the prior knowledge we have about the values theta might have. Okay, now this is all a bit abstract, but bear with me for a moment. We're going to give a concrete example to try to illustrate this. Okay, but just to get the notation out of the way. Now, if this is a conditional likelihood, of course we can have the joint likelihood. Okay, so the probability or density that x1, x2, blah 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 up to xn, and then theta, the random variable theta, what's the joint density or mass of all those variables, okay, taken together. Obviously, from our knowledge of probability, we know that the joint likelihood, and now here, maybe the notation is slightly inconsistent. Maybe I call this little f. Maybe it would have been better to call this big L. Okay, but let's just stick to the notation here. Big F, the joint likelihood. But again, big F represents that it's a density if everything is continuous. Okay, if all the variables are continuous, a density. If all the variables here are, well, okay, if all the variables here are discrete, but this theta, we assume it's continuous, right? We assume this G is a density. So that's why it makes sense to call this a likelihood. Okay, because here, if those are discrete and this one is continuous, well, strictly speaking, we don't have a density here. But anyway, what matters is really the definition of this joint likelihood. It will be simply the conditional likelihood of all the data given the parameter times the marginal density of the parameter. Okay, this just I think you know this, but just in general, f of the joint density of any variable x and y, okay, x and y, okay, is going to be the conditional of x given y, okay, x given y, whoops, times the marginal of y. Okay, and of course, if you can invert this relation and say that the conditional density of x given y is the joint divided by the marginal of y. Okay, so now we have the joint of all the observations and the theta. We can get, if we want, the marginal density of the observations. Okay, the vector of random variables x1 up to xn. Yes, as usual, if you want to get the marginals, you would grab the joint. Okay, this is the joint as is given here, and you integrate out the one of the variables, okay, to get the marginal of the other variable, or in this case the vector. Okay, so integrate out the d theta over its whole support. Of course, in a specific problem or situation, those bounds might not be minus infinity to infinity. They might be 0 to infinity or something else. Okay, it depends on the situation. So this is obviously is a general formula. Okay, so that would be the marginal density. But careful that, you know, of course, we call it marginal density, meaning it's the marginal density of all the x's, but it's still a joint density in the sense that it's the density of many variables at a time. It's just that we've integrated out the theta. Okay. Now we get to what we really care about, which is the posterior density of theta given the sample. Okay, because you see, here we have the conditional, okay, the conditional density or likelihood in general of the sample given theta. Okay, so given theta, what's the density of my sample? But in reality, what we're interested in is theta, the parameter, considered random. So what we really want is the inverse of this. Okay, we don't want the density of the sample given theta, we want the density of theta given the sample. Given I observed all my data, what is the new density of theta? Because said otherwise, here we start with no data. That's what we think theta is, or the distribution of theta. But now that we observe data, that obviously the data depends on theta, now we can update this idea of what the distribution of theta is in light of the data. Okay, so this is what is done here, and this is just by analogy to the Bayes theorem. Okay, we start with we started with likelihood of the data given theta, and we end up with likelihood of theta given the data. Okay, and this of course is just, this is again the joint. Okay, this is the same thing we had before. Okay, this is a joint, okay, given here. And at the bottom is of course the marginal, but the marginal of the sample, the whole sample. Okay, this here. Okay, just by definition, this gives you then the conditional, but the other way around, the conditional density of theta given the observations. Okay, but now just one word of interpretation, and then we go to an example. This posterior density is an updated density for theta, which now uses both the information contained in the data and the information contained in the prior. Okay, so this depends on both the data we've actually observed that gives us a lot of valuable information about theta, because the data is generated under theta. Okay, but obviously because the data is generated, the data follows a certain distribution that has theta as a parameter. Okay, so of course the data is influenced by theta, but also we're still using, so we're using the data, but we're still using the joint. Okay, so the joint still has an influence on the distribution of the posterior. Okay, if this is a bit abstract, bear with me. This example hopefully will make things a bit clearer. Okay, again, we'll go back to our recurring character Josephine. Okay, and again, we're interested in her adventures in the dating sphere. So she's been on a dating app for a while. Now, on the dating app, when she likes someone, that person might or might not like her back. So for Josephine, a relevant parameter is this. We're going to call it theta. And theta, we define it as the probability, even any given person, just taken at random, likes her back. Okay, so anyone might like her back or not. So we might say, okay, this probability, any given person likes her, that's our theta. Okay, this probability. But again, careful, we're under the Bayesian context. So we consider this probability to be an unknown to which we assign a certain probability distribution, describing the uncertainty we have about this probability, theta. Now, you see in the Bayesian context, Josephine might have some idea of what theta is, because she's been on the app for a while. Now we say here, she hasn't paid too much attention to the proportion of people who like her back, but still she's been using the app. So she has some intuitive idea of what theta is. Okay, it's probably more than a few percent based on her experience, but it's probably not too high either. So her prior idea of what theta is, she thinks it's around, okay, it's around 20%, but she's quite uncertain about the number. So you see, she assigns a certain probability distribution to what theta is. Okay, and she thinks, okay, with some likelihood it's around 20%, but I'm quite uncertain of what theta actually is. So it might be 30%, but I just think this is less likely. And you know, it might be 10%, but also I don't think that's too likely. Okay, and I don't think it's 5%. Okay, but it's still possible, but I don't think it's 5%. The probability someone likes me back. Okay, so so that's the context. Now there's a few questions here. What prior distribution would be reasonable here? Here, maybe a few choices are possible, but of course, it just needs to be bounded between 0 and 1, of course. Okay, so if theta is a random variable, you know, g theta should be 0, okay, outside the interval 0, 1, because of course the probability is between 0 and 1. For theta, you know, for theta not in 0, 1. Okay. Of course here, so maybe a uniform would be reasonable, although a uniform would be flat. Okay, so you might want to choose a uniform that has a mean at 20% and then say, okay, it's something like that. Although it's probably not the best choice, because here you're saying that 20% is as likely as, say, 25%, as likely at 30%, but then it drops to 0. Okay, so that doesn't make that much sense. It seems more reasonable to pick something like this, a distribution that's kind of smooth and as a peak at a certain value, maybe 20% here, if that's her preconceived idea of what the probability is, but then, you know, get smaller and smaller as you go away from 20% and on both directions. Okay, so something that looks a bit like this would seem reasonable. And in fact, that would be a beta distribution then, because, you know, the beta distribution, a beta with parameter alpha and beta, is, of course, you know, as support 0 and 1, but then you can pick the alphas and the betas such that the mean is something. In this case, we might pick the alphas and the betas such that the mean is 20%. And also based on alpha and beta, the variance will be more or less, you know, big. Okay, so you alter alpha and beta, you can keep the mean at 20%, but you can play around the variance. Okay, if your prior is more or less strong. Okay, if Josephine is very convinced that 20% is the right value, then she would have a prior that doesn't have a big variance because she's quite convinced that it's 20%. But if she's really very uncertain about this 20% thing, then she might pick one that has a whoops, that's not too good, a plot. Okay, that has a bigger variance around what she thinks is the true value, 20%. Okay, so she can play around the values of the parameters of the beta, which is our prior. Okay, so here, what prior distributor would be reasonable? Well, beta seems a good choice. Okay, with those alphas and beta that generate a mean of 20%. Okay, well, and what data could she start collecting to improve her knowledge of theta? Well, of course, she should just start recording whoever is liking her back. Okay, every time she sends a likes, maybe she keeps a log of how many likes she has sent, and then she keeps a log of how many likes she gets back. So she starts recording what interests us here, the proportion of people who like her back. Okay, so that's a setting. And of course, the point here is this: based on the data she's going to collect, it's going to update her view of what the parameter theta is, okay, based on the information collected. Okay, so let's solve this problem, but this is a kind of a specific context, okay, real life, if you will. But now let's just solve the problem generally. Assume you have an independent sample of random variables xi given theta, which are Bernoulli. Well, yes, because here this is what we would have. Every time she gets a like, the person can like her back. That would be a 1. Okay, xi equals 1. Okay, person likes her back. Or, of course, xi equals 0. The person does not like her back. Okay, so, and she sends here, n would be the number of likes she sends. Okay, and then xi is whether or not that like she sent generated a like back. Okay, so, and this has a certain probability. Now, what we're saying here is that given theta, xi is a Bernoulli theta because it's a trial that is either success or failure. Okay, and what we're saying is, let's model this theta to be a Bernoulli. Okay, Bernoulli, again, let's just solve this in the general case. Sorry, a beta, of course, a prior that is beta with parameters alpha and beta. In our case, in the case of Josephine, I mean, you'd pick alphas and betas such that the mean is 20%. Okay, what is the posterior distribution of theta? Hopefully the context is relatively clear here. Now it's a mathematical problem that we solve. For Bernoulli, the mass function, so here the x's note, of course, they're discrete, so they have a mass function. You can write it simply like that. Okay, the argument here, x, is the 0 or 1. Okay, I have a failure or success. Okay, so it's here. And theta is viewed as, of course, the parameter of the Bernoulli. Okay, so it's the probability of success. Okay, so that's the form of the probability mass function. You can then write the likelihood. That's the conditional likelihood of the data given a specific value for theta. It's just the product of all those things evaluated at all the little x1, x2, blah, blah, blah. Of course, those x1, x2, they only take 0, 1 values. Okay, so the product of all those things, okay, theta x1 times theta x2 times theta blah, blah, blah is going to be theta to the power of the sum. Okay, like careful here. This is theta to the power of this sum. Theta to the power of the sum. Okay, maybe it's the rendering here in the PDF is not the greatest, but yes, it's theta to the power of this. Okay, and on the other side, okay, 1 minus theta times 1 minus x1, 1 minus theta times 1 minus x2. Okay, in the end, you're gonna multiply n times, so you're gonna get 1 minus theta to the n, and then you're gonna multiply for every x, so you're gonna get minus, there's a minus here, minus the sum of all the x's. Okay, so that's our joint likelihood of the data given theta. So sorry, did I say joint? This is of course the conditional. Okay, now we get to the joint. Okay, the joint is obviously just the conditional times the prior. Okay, so you just rewrite this. Now you have the prior of a beta is just this general expression. Okay, here you see it's kind of nice. Things can go together because you have a theta to the power of something, and here again you have the theta to the power of something, so you can put them together. And same thing here, 1 minus theta to the power of something, 1 minus theta to the power of something, you put that something over here. Okay, so that would be your joint. Now you need the marginal, not too hard. You have the marginal mass function. Okay, by definition, you would integrate the joint with respect to the parameter here, theta, okay, that you don't want, because what you want is the joint of the x's. Okay, and okay, so you take the integral of this thing, but it's an easy integral because we've seen in one of the tutorial problems that this integral here, because this is just a constant, the integral from 0 to 1 of this, okay, you see with respect to theta, so the integrating variable here, of course, is theta. Okay, go back to the tutorial on problems on week 1, one of the first problems. This integral is very easy. It is just the gamma function, okay? The gamma function evaluated at this argument here times the gamma function evaluated at this expression over there, n minus blah, 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 plus beta. Okay, and then divide by, again, the gamma function, the sum of those two things, okay? The sum of x minus the sum of x, this disappears, and then you're left with n alpha beta. Okay, now, that's the marginal density. And you see, of course, it's the marginal density of the x's, so unsurprisingly, there's no theta here. Okay, but this we could have known from the beginning because we're integrating out theta. Okay, and then we get the posterior. So of course, the posterior of theta given the data is the joint divided by the marginal. And so it's just here, the joint, we have it. And then divide by the marginal. But you see, there's lots of terms that are going to cancel out, okay? Because this, we have it here. We divide it by the marginal, it disappears. And then what happens? Well, essentially, theta here, sorry, the yeah, okay, yeah, we have the yeah, well, the joint is just I'm sorry, I'm just too cluttered in my writing here. The joint is just right here. Okay, so then we are left with this that doesn't disappear. It's just there. The other one over there also doesn't disappear. It's just there. Okay, now some of the constants disappears, as I said. This disappears with this. Okay, but those, they are inverted. This one was on the bottom, but gets on top, and so on. But now you see, we highlight here in the colors that you might recognize this to be a density of something you know very well. It's again a beta. It's just that the parameters have been updated, because you have, see, the argument, because of course this is a density, this is the argument of the density. Okay, the theta is the argument of the density, in the sense that, you know, it's not g of x, it's g of theta. Okay, and so the theta is here. It is to the power of here a constant. Okay, we view this as a constant because it's the observations we've already observed. 1 minus theta to another constant, -1 here, and then you have exactly here the right constant here that makes this a beta distribution. Okay, and so you're done. Yeah, you can conclude that this posterior is something nice. It is the density of a beta, but careful with updated parameters. Okay, what we usually call alpha. To avoid confusion, let's call it alpha star here, just to mean that it's an updated. It's the sum of the x's plus the alpha of the prior. Okay, alpha is a parameter in the prior. Okay, and same thing, you have when we have an updated beta, okay, beta star, let's call it beta star, which is function of here the observed data and the old beta. Now, just a comment that this is not really a coincidence. It's actually quite common that the prior distribution, well, it has a name, you know, the prior distributions that result in posterior distributions that are of the same functional form as the prior, but with altered parameters, they're called conjugate priors. Okay, and this is very convenient because we obtain a distribution that we know very well, so we know what the mean of this distribution is, we know what the variance is, and so on. Okay, and so we here, I think we would say the beta is a conjugate prior for the Bernoulli, meaning that if you have a Bernoulli with a parameter that's a beta, you get the posterior that also is a beta. Okay, now just okay, as a comment, just here quickly, you know that the expected value of a beta is the alpha parameter divided by the alpha parameter plus the beta. Okay, let's call them alpha star here, alpha star here, alpha star here, just to mean it's those ones. What do you notice? The bigger the sum of the x's are, the bigger this will be, because on the numerator, bigger x means that it's going to make this increase. And on the denominator, you have the opposite. There's a minus sum. Okay, so if sum of x increases, well, actually, well, I'm saying, okay, in fact, alpha plus beta here, it cancels out, right? Like the denominator actually doesn't depend on the sum, but the numerator does in a linearly increasing manner. So the higher the sum of the x's, the higher your mean value for the expectation of this beta, which makes sense. If in our example of Josephine, she observes a lot of people who like her back. Okay, so most of those x's, or a high proportion of those x's, are 1, meaning someone likes her back. Then the mean of the posterior of the parameter distribution, the theta distribution, is going to be bigger, which makes sense. Okay, we have more data that says, okay, the proportion of people who like her back is big. Okay, so we update our belief that theta is actually bigger. Okay, but now maybe I'm getting slightly ahead of myself. Yeah, We're going to discuss this again in a second. Okay, but let's come back to the idea of parameter estimation. So because, okay, this is all fun, but okay, this whole week is about estimators, right? So, well, yeah, we can go back to our estimators because once we have a posterior for theta, so we have an idea of the whole distribution of the parameter, but you can extract from it an estimator, meaning our best guess of what theta would be from the posterior distribution. Okay, and here we don't get into too much detail here. Many choices would be possible because, of course, if you have a distribution, okay, what's your one best guess of where theta is if you have a whole distribution for it? Maybe you want to choose the expectation. Maybe you could choose the median. Maybe you could choose the mode. Of course, if it's a symmetric distribution, all those things are the same. But if it's not symmetrical, then they're not the same. Now here, we're not going to enter into competing Bayesian estimators. Okay, they all minimize a different loss function, but we're not going to get into that. We're just going to say for this unit, okay, what we call Bayes estimator is just the expectation. Okay, it's the expectation of this distribution here, the distribution of the, well, the expectation of the posterior distribution. This is what we call the estimator for theta. Our best guess of theta is based on this posterior distribution of theta. And so here, just to wrap up, if we go back to this example of Bernoulli observations that have a beta prior for the probability of success theta, what is the Bayes estimator in this setting? Well, as I said just now, is the expectation of the posterior, but the posterior is just beta with new parameters. Okay, so you see the posterior, the posterior distribution is beta with those parameters. The Bayes estimator, here you might want to call it big theta hat. It's the expectation of theta given the observation. So it's the expectation of the posterior distribution. It is this thing. As I said, it's linearly increasing in the sum of the x's. So the more successes you see, the higher is going to be your estimate or estimator of the probability of success theta. Now, here there's also another question. Can you express this estimator as a weighted average of the MLE estimator? Okay, if in the frequentist approach where theta is seen as a fixed quantity, okay, if you record a sample of successes and failures, you can estimate theta in the let's say conventional way. That's the MLE estimator, and this expectation of the and the expectation of the prior distribution, because of course, before collecting any data, you had some idea that your theta was somewhere. Okay, your prior distribution said, okay, maybe in the example of Josephine, 20%, but that was your expectation of the prior distribution, what you thought theta was before observing any data. Okay, so you can do that. Okay, you can express this new estimator, the Bayes estimator, as a weighted average. Okay, here just notice you have the sum of the xi plus alpha divided by something. Okay, if you multiply this by n divided by n, you haven't changed anything. That's the first bit. Don't forget the alpha. Same thing. You have the alpha here. You multiply it by alpha plus beta and you divide by alpha plus beta. This is just to highlight that yes, we have a weighted average of what? Of this is the MLE estimators. Okay, it's quite simple to prove that in a sequence of Bernoulli trials, if you estimate P, the probability of success, well, here we call it theta, but the probability of success, you estimate this by just, of course, the sum of the number of success divided by n. That's your both your method of moments and maximum likelihood estimator. Okay, here. Okay, you might want to call this x bar if you prefer. And on the other side, this is, of course, just the expectation of our prior for theta. Okay, because, of course, the prior was a beta alpha beta, so it's alpha divided by alpha plus beta. It's a weighted average in the sense that this is a certain percentage, and this is another percentage, but they sum to 1, obviously. Okay, this plus this equals 1, meaning you can view the Bayes estimator theta hat to be a weighted average of the sample mean, which is the MLE estimator, and your prior estimation of what theta is, which is the mean of the prior. But the point is, of course, that if n is very large, then of course this thing is going to be close to 100%, and you're giving a lot of weight to the data. If n is not so large, then this is not going to be so close to 1, and this is going to be bigger. So if n is small, you're going to give more weight to your prior, meaning you start with a certain belief, but if a lot of data is accumulated that goes against your belief, you're going to weigh this data much more in your final assessment of what theta is. Okay, so it makes perfect sense that we have a weighted average that gives more weight to the data if the sample is large, more weight to the prior if the sample is small. Okay, hopefully that makes a bit of sense, and I think that's the end of the Bayes estimator. I think it makes more sense. I'll just stop here so that there's a video for estimators, and I'll make a separate video for goodness of fit. Okay, so I'll stop here. Thanks so much for having followed me. If this is still a bit difficult, hopefully a few tutorial exercises should help you to do the drill yourself. Okay, and if you have any questions about this, of course, send them my way on the discussion forum. Okay, so I stop here. Bye-bye for now.